So in the last video, we spent some time talking about the equivalent conditions for stability and instability for equilibria of first-order systems as opposed to first-order, just a single first-order equation. And our main theorem was just basically stating that x bar is locally asymptotically stable if all the eigenvalues of the Jacobian matrix are less than 1, and unstable if there's some eigenvalue that's greater than 1. And this is basically a analog of the condition for first derivatives of basically the first derivative test for a first-order system. So if the first derivative is less than 1, or if the first derivative has magnitude greater than 1, that determines stability versus instability for first-order equation. And the equivalent thing is to look at the Jacobian matrix, which is the generalization of the first derivative to multivariable calculus. And so when that has an eigenvalue that's greater than 1, then it's unstable. And if all the eigenvalues are less than 1, then it is stable. The proof sketch basically followed the exact same scheme as the proof for the first derivative test. The difference is, of course, that you have to be slightly more careful with the eigenvalues, because you might have one eigenvalue that's less than 1 and another eigenvalue that's greater than 1. So in this case, we made use of the fact that if the spectral radius of a matrix is less than 1, then the limit as the matrix powers goes to 0 as t goes to infinity. On the other hand, if there's some eigenvalue greater than 1, then the component of that eigenvalue, the component of your starting vector x naught, the component that's with respect to the corresponding eigenvector will grow, at least for a while. Obviously, as you start leaving the small ball around your x bar, so as you leave the local region, your linearization breaks down. But the basic idea is that, and you can formalize this with the delta epsilon proof, that you still end up going further and further away. So I'm not going to spend too much time on that, since we did go through that proof pretty carefully. Instead, I'm going to spend some time on actually proving this, proving some jury conditions for the n equals 2 case. So here for theorem 2.10, we gave a lot of conditions that allow you to quickly determine, whether or not a 2 by 2 matrix has eigenvalues that are less than 1 or greater than 1. And basically, we are able to, because the characteristic polynomial of a 2 by 2 matrix is determined by its trace and determinant, we can actually write out the conditions in terms of trace and determinant, and both of those are relatively easy to compute for a 2 by 2 matrix. So let's go ahead and prove this 2 by 2 theorem 2.10. So first, since we're going to be using trace a lot and determinant a lot, let's set trace equal to tau and determinant equal to delta, determinant of j. So the characteristic equation of a 2 by 2 matrix is p of lambda is equal to lambda squared minus tau lambda plus delta. And this is something that you should recall from your linear algebra class. And of course, applying the quadratic equation, you get that the two eigenvalues are equal to tau plus or minus the square root of tau squared minus 4 delta over 2. Now, of course, there are several directions that we need to prove this. We need to prove the forward case. If the eigenvalues are all less than 1 in terms of magnitude, then you get this trace condition here. And you also need to prove the backward case. Just a moment. I think I erased. Yeah. Okay. Yeah. And you also need to prove the backward case, where if you have this condition here, then all the eigenvalues are less than 1. So let's do this in steps. So let's say forward case 1. So we're going to deal with the case where our assumption is that all the eigenvalues are less than 1. And we're going to additionally add the assumption that they're real, because it turns out that the proof is going to be slightly different depending on whether or not the eigenvalues are real or complex. So this in turn implies that tau squared minus 4 is greater than or equal to 4 delta, because tau squared minus 4 delta has to be greater than or equal to 0 in order for the eigenvalues to be real. Also, we have that tau is equal to lambda 1 plus lambda 2. So the absolute value of tau is less than or equal to lambda 1, the absolute value of lambda 1 plus the absolute value of lambda 2, which is less than 2. So that's by the triangle inequality. Furthermore, the function p of lambda is a parabola with vertex at tau over 2. So this is pretty easy to see. We have this equation up here, and this is clearly a quadratic equation, and so you end up getting a parabola. And with a little bit of work, you can see that the vertex is at tau over 2. And of course, we have zeros, and zeros at lambda 1 and lambda 2. Without lots of generality, let's say that lambda 2 is less than lambda 1. Okay? So we can obviously set it equal. So therefore, we know that minus 1 is less than lambda 2. Since both are minus 1 is less than lambda 2, is less than or equal to tau over 2, is less than or equal to lambda 1, is less than 1. If I draw out this parabola, it looks something like this, where this is lambda 1, say this is minus 1, this is 1, and let's say that this is tau over 2, and let's say this might, let me move this over slightly actually. So let's say this here is tau over 2, and let's say this is lambda 1, and this is lambda 2. Then your parabola looks something like that, where this is your vertex. And so this is p of lambda. Okay, but anyway, so we have that lambda 1 and lambda 2 are between minus 1 and 1, obviously. So we can use that to figure out that tau over 2, well, that's clearly less than 1. I mean, that's just a direct consequence of that. So we know that 4 is greater than tau squared, which is greater than or equal to 4 delta by our assumption up here. It's greater than or equal to 4 delta, which implies that delta is less than 1. So the determinant has to be less than 1, which was one of the things that, which is one of the things that has to be true for that. So 1 plus the determinant has to be less than 2, or the determinant has to be less than 1. Those are entirely equivalent. Also, we know that tau over 2 minus 1 is greater than tau over 2 minus lambda 1. How do we see that? Well, this is just the distance between tau over 2 and 1 versus the distance between tau over 2 and lambda 1. And so clearly, this distance is smaller than that distance. And of course, we also have the other one, which is that tau over 2 plus 1, or minus minus 1, the distance from minus 1, is greater than the distance from tau over 2 to lambda 2. And let's give ourselves a little more space. So now recall that the absolute value of tau is less than 2 from above by the triangle inequality. So we have that 1 minus tau over 2 is greater than, so we know, so because of that, we know that tau over 2 minus 1 is less than 0. Let's, because tau has absolute value less than 2, so this is a negative number. Which then implies that 1 minus tau over 2 is greater than tau over 2 minus lambda 1, or the absolute value of tau over 2 minus lambda 1. And that's taking this here and converting it, because we know that it's negative, and so we just multiply it by minus 1. And similarly, we know that 1 plus tau over 2, we know that that is positive. but that's greater than tau over 2 minus lambda 2. Well, we can put that together into 1 plus or minus tau over 2 is greater than tau over 2 minus lambda, just a moment, minus actually lambda I for either of the lambda i's. And this is, of course, because if you look at this parabola, well, tau over 2 is the same distance from either of the lambda 1 or lambda 2's, and here we have that, and so those two are equal. So 1 plus or minus tau over 2 is greater than the distance from tau over 2 to either one of the eigenvalues, just on different sides. So, but notice that means that tau over 2 minus lambda I is, we also know that that is equal to the square root of tau squared minus 4 delta over 2. That is, of course, just the consequence of looking at the quadratic equation formula earlier for the eigenvalues. But then, that implies that 1 minus tau over 2 is greater than the square root of tau squared minus 4 delta over 2. And with a little bit of manipulation, what we find is that that implies that if we square both sides, 1 minus the absolute value of tau plus tau squared over 4 is greater than tau squared minus 4 delta over 4, which implies that 1 minus the absolute value of tau is greater than minus delta. And so that gives 1 plus delta is greater than the absolute value of tau, which is, of course, if you flip that, that's just tau is less than, the absolute value of that is less than 1 plus delta. Furthermore, we also have that delta is equal to lambda 1, lambda 2. So that means that the absolute value of delta, let me rewrite that, the absolute value of delta is less than 1, which implies that 1 plus delta is less than 2. Okay, so that proves the condition. That proves these conditions in the case where you have all the eigenvalues are less than 1, and the eigenvalues are real. Now, we also need to prove the case when the eigenvalues are imaginary, and it turns out we need a slightly different analysis for that. So this is for case 2. So we have lambda I is less than 1, and if the eigenvalues are imaginary, then they're complex conjugates of each other, because we have real coefficients. So these are complex conjugates. Well, when we know that tau squared is less than 4 delta, because otherwise it wouldn't be, because if not, then it wouldn't be complex. And when we write that out, that means that lambda 1, comma 2 is equal to tau over 2 plus or minus I times the square root of I times the square root of 4 delta minus tau squared. Note we flipped it because we took the I out of the square root, divided by 2, which implies that the norm of lambda I for either of them is just equal to tau squared over 4 plus delta minus tau squared over 4, which is just equal to delta. Okay, and that implies that 0 is less than delta is less than 1. But of course we know that tau is less than the 2 times the square root of delta by just taking the square root of this thing here, less than the square root of delta, which of course is less than or equal to 1 plus delta because delta is between 0 and 1, and so 1 is clearly larger than so this is actually a consequence of this inequality, a squared plus b squared is greater than or equal to ab, which is pretty easy to check. And together that implies that tau is less than 1 plus delta is less than 2, which proves this forward case as well. And we now have two different backwards cases. So that was starting from the assumption that our eigenvalues had magnitude less than 1. What if we have the other condition? So what if we already have the jury condition on trace and determinant, and we want to say something about the eigenvalues? So let's do backward case 1. Case 1. In the backward case 1, you know that tau is less than 1 plus delta is less than 2. And we know that lambda I are, and suppose that we're in the real case, so we have tau squared is greater than or equal to 4 delta. So we're going to let lambda 1 be equal to tau over 2 plus the square root of tau squared minus 4 delta over 2. And let's say that call lambda 2 be equal to tau over 2 minus the square root of tau squared minus 4 delta over 2. Delta over 2. So lambda 2 is less than or equal to lambda 1. Well, note that the absolute value of tau is less than 1 plus delta. We know that. And so if we rearrange this slightly, we get 1 minus the absolute value of tau is greater than minus delta. And if you add tau squared over 4 to both sides, you can factor that out. It's just a square of this thing squared is greater than tau squared over 4. So you add tau squared over 4 to both sides, minus delta, which is greater than or equal to 0. But now, since it's greater than or equal to 0, you can take the square root of both sides now. The 1 minus the square root of tau over 2, or sorry, 1 minus the absolute value of tau over 2 is greater than the square root of tau squared plus, minus 4 delta minus 4 delta divided by 2. Let's give ourselves a little bit more space. Yeah, so that's over 2, which we can rearrange to being 1 is greater than tau, the absolute value of tau over 2, plus square root of tau squared minus 4 delta over 2. And now this, of course, is greater than or equal to lambda 1. And we know that minus 1 is less than minus the absolute value of tau over 2 minus the square root of tau squared minus 4 delta over 2, which is less than or equal to lambda 2. So we get that minus 1 is less than lambda 2 is less than or equal to lambda 1 is less than 1, as we want. And the other backward case is actually even easier. So the other backward case, backward case 2, is, well, if you have tau is less than 1 plus delta is less than 2, and our lambda I are complex conjugates, well, then we know that lambda I squared is equal to delta is less than 1. And that finishes the proof. So that was a lot of algebra and notation. Basically, this is what it takes in order to actually show that you have all your eigenvalues have magnitude less than 1, or that you have eigenvalues that have magnitude greater than 1. It's for this reason that we're not actually going to take the time and go through the proofs for the higher degree conditions. So for an n equals 3, it turns out that you can do something similar. So it's a very long analysis, case-by-case analysis, and you can do something similar until that if these 3 conditions are the case, then you know that there is some that all the eigenvalues have lambda I less than 1. And you can say this in general for a polynomial. You don't have to say this for the eigenvalues of a matrix. But of course, those are entirely equivalent, since for any matrix you have a characteristic polynomial, and for any characteristic polynomial you can construct a matrix with that polynomial. And the case for n, arbitrary n is even more complicated. It turns out there is a necessary and sufficient condition, so you can prove the same sort of thing, but then that makes this condition 3 really, really unwieldy. And so instead, what we've given you here in theorem 2.12 is just a necessary but not sufficient condition. So if you know that the eigenvalues all have value less than 1, then this must be true. Then all three of these things must be true. But even if these three things are true, it doesn't necessarily mean that the eigenvalues are less than 1. Let's actually, and then we just define that hyperbolic or non-hyperbolic by the eigenvalues instead of just by the first derivative. So if you think of the Jacobian as the generalized first derivative, the eigenvalues of that determine whether or not something is hyperbolic. Okay, so that was a lot of theory. Let's go ahead and give a biological example, since this is an introduction to mathematical biology, and biological examples are fun. So let's consider a predator-prey system. So we have, so maybe you could think of it as wolves and deer, I think is the classic one, but any sort of predator-prey system where the prey is, you can imagine that it's some herbivore, and so it grows depending on how much it grows logistically in your environment, and you have some predator that preys on the number of current prey. So if we write this mathematically, we have some x sub t plus 1 is equal to x sub t a minus x sub t minus y sub t. So this is logistic growth for a greater than 0. This is one of the variants of logistic growth. So this here is our prey. So it just it tries to grow logistically, but you'll notice that we have this y of t term, which is going to be our predator, which is going to be eating it up. So for the more predators you have, the slower the growth rate of the prey because they get eaten. So the predators are going to be growing at the rate y sub t plus 1 is equal to y sub t times b plus x sub t for b greater than 0, less than 1. So the growth rate of the predators is mostly just dependent on the number of prey that are there. If there are more prey, well then the predator grows more quickly. Okay, so this is the system of first order equations. You can set them all equal and find the equilibria. So you can set the x sub t plus 1 equal to x and x sub y sub t plus 1 equal to y sub t. And you end up getting 3 equilibria. Those are 0, 0. So obviously if you don't have any prey or any predators, well then that is an equilibrium. There's another equilibrium at a minus 1, 0. So this is when you only have prey and no predators in the system. And then of course there's the more interesting stable equilibrium, which I'm going to call x bar with y bar, which is equal to 1 minus b, a plus b minus 2, when you have both predators and prey in an equilibrium. Now, how do we get the Jacobian matrix? Well, the Jacobian matrix is equal to d dx of the first equation, so that's x times a minus x minus y, d dy of the first equation, x times a minus x minus y, divided by the derivative of, sorry, these are partial derivatives, partial derivative with respect to, to x of the second equation, so that's y times b plus x, and the partial derivative with respect to y of the second equation, so that's y times b plus x. And when you compute that, this Jacobian is then equal to a minus 2x minus y minus x, and y and b plus x. Okay, so now that we have that, we can talk about the Jacobians at each of our equilibrium points, and then use the jury conditions to figure out whether or not things are stable. So for j of 0, 0, well, this is the easiest case. This Jacobian is just a 0, 0, b. And then we also have j of a, the other equilibrium, a minus 1, 0. So that, when you plug that in, it's going to be 2 minus a, 1 minus a, 0, and a plus b minus 1. And then we also have the jury condition, the Jacobian of the final equilibrium, which is a bit more complicated, x bar, y bar. And when you plug that in, and this is a little bit of algebra, but it's not too bad, that's b minus x bar, y bar, and 1. So let's examine each of these cases individually. So in the very first case, well, the eigenvalues are super simple. Lambda 1 and 2 are just equal to a and b. So since 0 is less than b is less than 1, so b is always less than 1, has magnitude less than 1 anyway, 0, 0 is locally asymptotically stable, if a is less than 1. So intuitively, everything dies. So basically, the growth rate of the prey animal, X, like the deer, for example, doesn't grow fast enough that even if you didn't have any predators at all, it would die out. So the fitness of this animal isn't particularly interesting in the case when a is less than 1. So that's a not so interesting case. In the second case, lambda 1 and 2 are equal to 2 minus a and a plus b minus 1, since this is a triangular matrix. But in this particular case, we just need that both of these have magnitude less than 1. So we need 1 is less than a is less than 2 minus b to be locally asymptotically stable and non-negative. Note that we can be slightly outside of this parameter range if we allow for having negative prey or negative predators, but that's not biological, so we're going to have both conditions for stability and also non-negativity. And so in this case, your prey survives, but predator goes extinct. And the last case is the one where we do need some jury conditions. So after some algebra using the jury conditions for n is equal to 2, we find that 2 is less than a plus b is less than 3 to be locally asymptotically stable and non-negative. And so here, the prey survives and predator survives. Okay, and so in this case, we actually you can do it directly by computing the eigenvalues, or you can use the jury conditions that we discussed here in Theorem 2.10 and just check the tracing determinant, which is a little bit more straightforward. Okay, so that's about it for this video. We went through some of the various jury conditions, as well as proved it for the case of n equals 2, and gave this example in the case of n equals 2, where the first thing you do is you find your equilibria, then you find your Jacobian matrix, and then you see what the eigenvalues of the Jacobian matrix are, and that determines the local asymptotic stability, or whether it's unstable for each of those equilibria. Thank you very much, and I'll see you in class.